Thank you for having me. I'm glad to be here, presenting to you guys, talking to you guys with regards to data center cooling and AI. I want to first of all just preface this conversation we're going to have with two things. One being that this is not an overly technical presentation as such. It's really about strategy, looking at where data centers are going, where cooling is going to fit into that space, particularly around AI and the things you can do around that today for the future. And the second thing is, for the purists out there, there is a difference between AI and machine learning, but we will just be using the two terms interchangeably just for this presentation. So my name is Jonas again. I work for Flax Group. The title of the presentation is The Evolution of Data Center Cooling, Harnessing the Power of Artificial Intelligence. So, is there a need for evolution, really? Well, let's look at the demand for computing power. We all know about data explosion. We've been talking about that and experiencing that for many years. The whole scenario around Moore's law, where you have chips on a transistor space doubling every 2 years, and then obviously that creates a massive explosion. So now, apparently, according to some analysts, the current world has around 97 zettabytes of data, and in 2025. It will still be 97 zettabytes of data, but only for machines, so IoT. So you can imagine the total amount of data in 2025 moving forward. So at some point, we'll be talking about yottabytes, not zettabytes, which is about 1,000 zettabytes. So it's growing immensely. And so that really leads me on to digital transformation. Yes, people were talking about digital transformation for many years, but over the last few years, particularly around the issue around COVID and the pandemic, every company now wants to be a digital company. Everyone wants to be online. Everyone wants to provide, client interfaces with online platforms just to be able to get business done. And so that really leads me on to cloud computing, where that's been an explosion because you have all of these digital transformation initiatives going onto the cloud. And there's only a few cloud computing companies, but they have exploded in terms of hyperscale activity. And obviously that's given a direct result into the explosion of co-location companies globally. And that's been, moved into the AI and the machine learning to really facilitate that. Everyone's talking about AI now. ChatGPT has brought AI into the consciousness of the average person around the world. And everything seems to be related to AI in some shape or form. And then you have emerging tech. So everything's a tech. You have fintech, health tech, retail tech, pro tech, edutech, biotech, clean tech. It's almost like there's tech emerging every single day. But it's really about new platforms to provide the right services to the clients that need that. And all of that needs to be secure. So as much as cybersecurity has been around for a very long time, now it's even more potent because on the other side of all of this activity is hacking and, espionage, industrial espionage, governments. And so even cybersecurity is demanding more and more computing power. And so you've got all of that happening, but at the same time, on the flip side, you have concerns around the environment and efficiency. So all of these data centers are utilizing so much energy. It's unbelievable. Everyone knows that. It impacts carbon footprints, and then there's this whole idea of inefficient cooling, not to say that the cooling infrastructure is particularly inefficient, but how data centers are designed and how the workloads are so variable when it comes to the server that it creates inefficiency in some shape or form. And you have electronic waste where, many servers and the various equipment are constantly just utilized and removed and put into landfills or maybe go into the circular economy. But again, e-waste is a big thing. And you have overbuilding, where consultants have to specify a particular data center based on the max workload. And also based on, the future-proofing of data center from an immediate perspective. And so you have to overbuild, you have to overspec. But where is the sweet spot where you can specify a data center based on the actual needs of that particular data center? Who knows? And so how can we find out? And then finally, you have waste heat as well. It's like so much heat is coming out District heating is a big thing. It is something that is in Europe, particularly. But how much heat is the right amount of heat to be used for district heating? So these are the scenarios where you have so much demand for computing power, but on the other side, you have concerns for the environment. How do you square that circle? How do you manage that conundrum, as it were? So if you go back to basics, I know I'm maybe teaching some of you to suck eggs here, but if you look at just, traditional cooling in a sense, and when I say traditional cooling, I mean just cooling methodologies in today's data centers, particularly in the colo space and the owner-managed data centers. So a lot of these products or infrastructure, FLAC do. So you have your precision crack units, you have CRAs and fan walls within the white space, you have chilled water systems within the grey space on top of the roof or outside, heat rejection systems that are in place. And in terms of distribution of heat, you have your cold hour and hot hour containments. And now we're moving towards a hybrid cooling environment where you would mix in liquid and air cooling scenarios. And all of that is managed in today's environment with cooling control systems that would link into BMSs, EMSs, and DSIM solutions. So all of these different technologies and methodologies has been effective over the last few years. So free cooling time has been increasing. Partial PUE has been falling. We're now at a stage where if you design the cooling infrastructure right, you'd always get it sub 1.1 partial PUE. So that's a great thing. It used to be at 1.8, and then it went to 1.5, and now we're really getting down. And then obviously efficiency is increasing, and that's creating a more cost-effective data center infrastructure environment. So these are good things that traditional cooling has benefited us over the years. But nevertheless, there are challenges. And when you look at these challenges, one of them is inefficiency of the variable workloads. Each server has a workload that can be working at different speeds at different times. And so as much as traditional cooling can handle a specific maximum workload, inefficiency occurs during periods of lower server activity. And so cooling may continue to operate at a high capacity, even though the workload is reduced. So all of that just creates unnecessary energy consumption. And then you also have limited adaptability for dynamic environments. So traditional cooling may struggle to adapt quickly to the rapid changes in conditions, whether it's fluctuation of server loads or whether it's quick changes in equipment configurations or evolving operational demands. All of this can challenge the adaptability of a fixed or static cooling environment. Now, we've made lots of progress, as I said earlier, with cold hour and hot hour containment systems. But there's still uneven heat distribution, only because, again, the server loads are constantly changing. So how do we grasp that bit? How do we get to a point where there is absolutely no uneven heat distribution? And again, that's an issue that we have to sort of tackle. And I mentioned about overbuilding before, where we over-specify. And again, it makes sense. We have to plan against the maximum server workloads. We have to plan against the immediate future-proofing of a particular data center. But, all of that overbuilding is an issue when it comes to space and resource. It impacts CapEx, OpEx, return on investment, only because most data centers are always underutilized with such a massive infrastructure, particularly around redundancy systems as well. And then finally, we have the issue around limited predictive capabilities. Yes, we talk about predictive maintenance. And yes, we have some form of limited prediction of what may go wrong, but it's not precise. It's very difficult to be precise in a static environment because at the end of the day, without the ability to anticipate temperature trends, potential heat surges, these systems are reactive and not proactive. So how do we address these things? So when you look at overall, you've got this demand for computer power that's never ending. You've got traditional cooling infrastructure that has gone some way to achieve efficiency. And when I say traditional, it also includes liquid cooling as well, hybrid cooling. But nevertheless, it's only some way it can get to, as much as that is efficient. How do we go through that transition from a static rule-based approach to cooling where it often struggles with the complexity of today's computing environment, to something more data-driven, something where the decision-making approach is intelligent. It uses algorithms and machine learning. And that's where AI comes in. Now, I know AI, we talk about it. AI is used for building cars. It's used for discovering new drugs. It's used for relating to different customers in different languages, to understand the world we live in even more so than we can ever imagine. But AI also gives us the ability to really look at unparalleled efficiency gains, accuracy, and cost savings. But how can we do this? So here are some of the benefits. Predictive analytics. So if we get AI right, it can leverage predictive analytics to anticipate the future changes in workloads. Again, the key thing here is server workloads. They work at different levels at different times. If we can predict how that works, analyze it with historical data, identify trends, then AI can forecast potential surges or declines in workload demand. And so if we can do that in real time, then a difference can be made. And if we're able to predict that, then we can also adjust the cooling itself. So, AI can actually do dynamic adjustments rather than static adjustments, and all of this can happen in real time. It can predict changes in temperature based on workload patterns. And all of this can be modified. All the cooling parameters can be modified autonomously without any intervention of people. And so such parameters can be modified like air speed, airflow direction, chilled water supply, just to get temperature into the optimum range. And then when you've done all that, how do you then allocate resources, workloads? So for example, if AI continues to monitor and analyze data center workloads and temperature patterns, then they can allocate it to different data centers or different servers within the data center. So if you look at an example where you've got, let's say you have a cluster of edge data centers around the world, and they're in different time zones. And obviously the cost of electricity, kilowatt hour, could be different at different times in different countries. Then as certain workloads come in, they can be assigned to a different data center in a different country. So that workload per kilowatt can be a lot cost effective for that particular data center. That can happen outside of the country, but it can also happen within the same data center. And all of this is based on real-time assessments that are dynamically allocating computer resources by adjusting these patterns of cooling, whether it's in a different data center or the same data center. And all of this means that you can precisely align the actual demand, and that therefore preventing overcooling. Now, can data centers or can the cooling infrastructure within data centers self-heal? Can AI be used to detect anomalies and by autonomously taking corrective action to address cooling inefficiencies and equipment failures? All of this reducing downtime and minimizing manual intervention. Can that happen? It started to happen in hyperscale spaces. Can it start happening in the co-location or the owner managed data center spaces? And we've talked earlier about district heating. And again, waste recovery. How can we identify and utilize very, very clearly specific waste heat generated by data centers and then redirect them to all kinds of purposes? But being very specific.
Jonas. Sorry, I'm so sorry to interrupt you. We've just had a couple of questions. We can't see your presentation. I don't know if you were intending to share your screen or...
Right. Okay. Did you see how long has that been?
The whole still... Sorry, yeah, we've not been able to see any of your slides so far.
Really? Okay. Let's see. Bear with me a second.
I'm sorry about this. No,
it's interesting. Let me unshare and share again. Right.
Perfect. Yeah, we can see them now. Thank you.
It's interesting. Okay. Right. Right. So you can see everything I've spoken about so far on the left-hand side, right? On the benefits.
Yes.
Right?
Yeah. We can see them all. Thank you.
All right. Cool. So thanks for letting me know. So future trends then. Bear with me a second. So edge is a big thing. It started to emerge in a big way. Now, edge data centers are slightly different from normal data centers in the terms that they have space constraints. They also are impacted by variable workloads in a bigger way. Because they're closer to the user, and also environmental conditions. So AI can make a huge difference to make these data centers, smaller, more accessible, nearer to the user in all kinds of environments. And when it comes to decentralization of cooling architectures, data centers typically, or cooling infrastructures typically, is centralized, and slowly started to move nearer and nearer to the server. So now we're at the hybrid cooling scenario where you have rear-door cooling, on-rack cooling, or in-rack cooling, where it's closer to the server, and at some point it's going to be liquid cooling within the server. So these decentralized cooling architectures and hybrid cooling strategies, how will they relate? How will they create a scenario where AI can make it optimal, rather than they almost working separately, as it were? And all of this can be dealt with in an autonomous fashion. Decisions need to be made. How does AI make those decisions when they see scenarios that need to change, as it were? So it's a case of really, advanced machine learning models can assess real-time conditions, predict future workload demands, and autonomously adjust cooling parameters to optimize energy efficiency. Now, thermal storage systems used to be a thing, and it still is within certain hyperscale, where you have all of this water stored and utilized depending on the cooling scenario. It's not really used as much within the co-location space, but with AI, then the thermal systems can come to the fore, because now you're intelligently, enabling heat management in a big way. So they can again predict the analytics of what's happening in the cooling space and allow data centers to store and release heat strategically, contributing obviously to energy efficiency and cost savings as well. And finally, where does quantum computing come into it? We're not there yet. It's still in the research phase. But if AI can get us, when it comes to efficiency and productivity up to a certain point, then can quantum computing, the algorithms that can create, even take us further, where we get as close to perfect efficiency as possible? I mean, these are questions that we're asking, can we do this? But as we see hyperscale go down this road, it's something that is definitely possible and something that can be incorporated within co-location and medium-sized data centers. So here's an example of the DeepMind case study in 2016, whereby if you see the four quadrants, you've got the top left as one, and then it goes round to the bottom left as stage 4. And this is a very simple scenario. A lot has happened since 2016. But DeepMind's AlphaGo, which is the cloud-based machine learning algorithm, would interact with one of Google's data centers. And the focus here is purely just energy efficiency, energy consumption. That's all it dealt with. Whilst AI of today, you can deal with a lot of other goals. But in this scenario, every 5 minutes, the cloud-based AI, i.e. AlphaGo, will take a snapshot of the data center cooling system using thousands of sensors. And then stage 2, that information is fed into DeepMind's neural networks, and all the training and calculations are done. And they predict how different combinations of potential actions will affect the future energy consumption. Again, it's just about energy consumption. So the third stage is the AI system, i.e. AlphaGo, will identify which actions will minimize the energy consumption, whilst at the same time satisfying a robust set of safety constraints. We don't want to go too far and then machines stop working because we're purely looking for energy consumption. So there has to be that level of safety constraints. And then finally, this action is then sent back to a data center, which is then verified by the local control system, and it's implemented. And then the cycle starts again every 5 minutes. And so this apparently brought the cost of energy down by 40% and the PUE by 15%. So this is just an example of what you can do within your data center. But there's so much more that you can do. So now we know what's out there. what can be done. A lot of companies are out there that have AI algorithms, smaller companies. Companies like ourselves are developing AI via our control systems. So the technology is out there, but how do you prepare for AI within your data center? So here's your data center. The main focus is historical data. That's basically the everything based around what you need to do. How do you capture data? How do you store data? How do you arrange data? And how do you prepare this data for when AI comes along to utilize that pool of information or data to be able to train to then be making decisions accordingly? So here's some examples of some parameters which are very important, and whether it's temperature, humidity, power consumption, weather conditions, you can see all of them there. The key thing is that you're getting this data and you're timestamping this data, and you're looking for interactions. So, for example, if the server load is a certain level at a certain point in time, what is happening with the power consumption or the temperature and humidity in the data center? What was the weather conditions at that particular time? How was the infrastructure heat mapped at that particular time? So you're trying to get as much information in real time as possible just to be stored, because that will be your training ground for the AI algorithm once that comes on board. And so the focus here is, what sensors do you have? Now, I read somewhere that the typical horn for a typical co-location data center, to be able to get enough information to accurately train AI systems in the future, is about 2,000 sensors. So whether it's sensors within units, within equipment, looking at the components of equipment, whether it's within the white space, outside of the white space, in the gray space, there's so many forms of data that can be got through different monitoring systems. So that's essentially it. When you think about the data center space itself, it's exploding. We know it's exploding. We know that needs to be tempered with environmental needs. Now, the traditional cooling does work, whether it's liquid cooling, air cooling, combination of both, hybrid. It does work, but so much more can be done. Now, AI does present a whole new world in productivity. The question is, are we ready? And how do we prepare our data centers to gather the right data today so that it can be trained tomorrow? And lastly, I've got to plug the company I work for. We obviously do cooling. We are one of the largest cooling companies in the world. We have the broadest form of products across data centers, industrial, commercial, residential. Our focus, certainly within the data center team, is to find solutions with our clients, with our largest clients, to make sure that effectively, efficiently, and that we can walk with them into the future. Thank you very much.
Thanks so much, Jonas. Thanks so much. I'm wondering if you'd be happy for us to share your slides with the audience, if that's as in we'll send them an email with it. Maybe would that be okay? As we immerse the cuff. Perfect, wonderful. So for everyone watching, we can easily share those slides with you for the first part of that we missed. So sorry about that. Thank you so much, Jonas. That was great. Just a couple of questions just before we move on to the next session. So obviously. And again, we've talked about this yesterday, we'll talk about it today and tomorrow. AI is very much an emerging tech in terms of how we're going to use it, how we're going to make the most of it. What kind of feedback are you getting when you're talking to, data center owners and operators out there in how ready they are, how much they want to adopt AI, to help optimize the operations? And how do you see what are going to be the challenges for them down the road as AI develops?
Yeah, it's a good question. These data center operators are business people. Essentially, if you look at colo, it's essentially technical real estate, and so everyone's looking at bottom line, and everyone's also looking at immediate bottom line. Because of the explosion of data centers, the focus is to build. Where can I get powered land? How can I start building data centers? How can I service our clients, their clients, which tend to be, the hyperscale guys anyway.
Yeah.
So we're in this massive growth phase, and a lot of companies are thinking, well, let me just build first. right? Let me get the client in, and then we can start worrying. And then you have this split between, well, what belongs to the colo and what belongs to the client. And, how much power does the client have to say, I need these in place because I want to utilize AI relative to, the colo. So you still have that conundrum there. I think that the thinking is, let's start building. And then, at some point down the line, we'll start to invest in AI. Yeah. AI is an investment. It's an investment fund-wise. It's also an investment in terms of the way you manage data centers and how you manage vendors that are involved in data centers, whether it's cooling, electrics, what have you. And so there's a big job there. The first thing they have to do is, obviously, as I said, is gather that data. But the second bit is to start thinking of your machine learning DevOps. What is that going to look like? What is your pipeline, your DevOps pipeline, to get to where AI is? And one of the things that I could start thinking about is DSIM and BMS and control systems, because that is the closest, or that's the interface between the physical infrastructure and AI ultimately. Is, your DSIM, your building management systems, your control systems, your environmental management systems. And it's talking to these vendors and saying, how can we, get the right information? What does arranging that information, storing that information look like? What is the standard we can use so that it's best available for training? And then start talking to some AI practitioners that exist today. Just conversations, just to understand what the pathway could look like. And one final thing is that you can either utilize companies out there, you could do it yourself, utilizing vendors like Flat, and other vendors. It really does depend on which way you want to go, and obviously the cost base as well.
Again, it's going back to that, having a conversation, not working in silos, really going with talking to vendors and talking and finding the best way forward. Just quickly, if I can, squeeze one more question in from the audience before we move on. How do you see the impact of heat reuse and AI?
Yeah, it's a good question. I think theoretically, I think, AI, as long as it's designed properly, the whole data center is designed properly, then heat reuse can be 100%. In practical terms, it's, reuse where? We're talking low grade heat. How quickly can you use it? And how close is where it can be used is, what does district heating look like? Now you're going into wider infrastructure. And Europe is ahead. So countries like the Netherlands are ahead in terms of its district heating infrastructure, particularly in the metropolitan areas. But then, you talk about thermal storage systems, where you don't necessarily need to reuse it straight away. What does heat storage, look like? So there are many practical and mechanical elements to this that need to be considered. But from an AI theoretical perspective, all the heat can be reused. It's just how you want to reuse it, depending on where your data center is located.
Yeah, I suppose that's the key word, theoretical at the moment. We've got lots of opportunities ahead. Thank you so much, Jonas.